In this section, I'm going to talk to you about alkenes and alkynes. And this is just now looking at the number of double or triple bonds that we find in different types of organic compounds. Alkenes and alkynes are called unsaturated carbon compounds, and that's because they are not saturated with hydrogen atoms. So if we look at a general structure of a carbon for an alkane, we have the carbon is going to be attached to 4 different hydrogen atoms. Kind of using these dashed lines in order to kind of show you the difference between a hydrogen, maybe kind of more three-dimensionally. This would be going inside the screen, and this would be kind of popping out at you through the screen, and these are in the plane of the paper. But here we have this carbon is going to be attached to 4 things, so this would be saturated. And here, this carbon, instead of being saturated, we're going to use actually these kind of side p orbitals. These are unhybridized p orbitals that are being used to create new bonds. So this is an example. These are being shown here and taken out. Here we have that sigma bond that's been removed, and then we have the 2 pi bonds. So this is an alkyne that's being shown here, and these are unhybridized p orbitals. Shown in purple and that blue. So this is one set of unhybridized p orbitals. The other set of unhybridized p orbitals, so this is sp hybridized, and also that carbon is sp hybridized. That initial sigma bond is an sp to sp hybrid bond, and the double bond, these are pi bonds. These are from the unhybridized p orbitals. When we look at these unsaturated compounds, we are essentially with alkanes, we have a certain number of hydrogens. When we have an alkene, we're replacing the hydrogens with a double bond. And then when we go to alkynes, we're replacing another set of hydrogens with another pi bond to form that triple bond. So you can see that is just kind of a formula for we are reducing the number of hydrogens, and that's why they get their name as unhybridized. We also look at some of the general structures for alkenes. As I mentioned before, in order to get that double bond, we are going to have to unhybridize one of those p orbitals in order to get that bond above and below the carbons. So we're going to be, alkenes are going to be sp2 hybridized. They're going to be trigonal planar, so they're flat with 120 degree bond angles. And again, those bond angles and the size of the bonds are a little shorter than signal. The length of the bond is a little shorter at 1.34 angstroms compared to the single bonded carbons. And the pi bond also locks the geometry. And we'll talk about that when we're talking about cis or trans isomers just in a moment here. So here are 2 different formations of around the double bond. We can have cis, which is another way of saying cis or same, and trans or opposite. And this is describing where the larger molecular weight elements are attached to that double bond. So if we look at the version on the left, we can see this double bond here between the 2nd and 3rd carbon, and it's attached on the top to an element with a higher molecular weight on top versus the hydrogen on the bottom. And in the 3rd carbon is attached on top again to a higher molecular weight element on the top versus the bottom. So these higher molecular weight elements are on the same side, and so this is a cis element. And on the right side, we see the double bond, and on the carbon on the left, we see that single bond, that higher molecular weight element or atomic weight element is on the top, but on the right side of the double bond, we can see that it's attached to the bottom. So that carbon has a higher atomic mass than hydrogen, so that's what gets priority in naming this. And those elements are on the opposite sides of the bond. We can't flip-flop these without some chemical processes or chemical change that would happen. So that's why these are named differently, and we'll talk about naming in a little bit as well. But this is going to define and determine which side of the bond that we're on. So I want you to think about this. I'm not going to have you build this. If you have a model kit, feel free to build one of these. But otherwise, we're not necessarily going to do that. But what I would like you to do is predict which of these would have a higher boiling point. Why do you think that might be? We're going to talk about it in just a second, but make a prediction. Think about what things might attribute to or change that boiling point. Between these two elements, the element that would be expected to have the higher boiling point would actually be the trans conformation, and that is because if you were to make this out with a model kit, you would probably notice that it's really flat and straight because of how these are oriented between each other. And that orientation allows these to lay down on top of each other and have more intermolecular force interactions, specifically the van der Waals or London dispersion forces. Where this bent form, especially when we get longer and longer chains, that kind of puts a kink in the chain, and it's harder to lay those down on top of each other. You'll also maybe notice this if you've heard of trans fats. Typically, trans fats are solid at room temperature, where their cis version would be a liquid, and that's partially because of the way that these lay down on each other and will have different melting and boiling points. Here's another example of a halogenated alkene where we have two chlorine groups attached to an alkene, and you can see that the left version here is cis, or it's the same side, and the right version is trans, where that chlorine is on opposite sides of the double bond. So this would be named 1,2-dichloroethane because we have an ethyl group, and it's called ethene because the ene ending, because it has a double bond, and we have two chlorines on the first and second carbon. So what we can see here in terms of the physical properties are that the boiling point for the cis version is 60 degrees versus the trans version is 47 degrees Celsius. So we have a higher boiling point and a lower boiling point for the trans version. And again, these will have different types of chemical and physical properties because their dipole moments are different. We have differences. These dipoles, they cancel out versus the ones with the cis. So if we look at this partial negative charge and a partial positive, if I draw an arrow that represents the directionality of where those electrons are pulled, and we have a partial positive, partial negative, that arrow here. So that overall net, if I add those together, the net charge is going to look more something like this. So we'll have that net charge. Sorry, I'll make it a little bigger because it'll actually be adding those together in that downward direction. So the net dipole moment is going to be negative more on the bottom part of the element, and then closer to that negative positive charge is closer to this carbon-carbon group. Now, if we look at this other group, we have a partial negative on the outsides and these partial positives in the middle. And those dipole moments, if we are going to add things together that are kind of in opposite directions, will have no overall net dipole moment because we are going to kind of pull these in opposite directions, as you can see with the arrows. So because of that less of a dipole moment, that boiling point is actually going to be reduced in this situation. For some of your homework this week, we're going to go through naming, and I have a naming handout that kind of walks through some of the systematic mechanisms for naming these kinds of alkenes and alkynes, and I'll keep that in that section, but just so you know that we'll go through some of those things to talk about naming and how those different compounds are named appropriately. Under normal situations, these two different isomers don't interconvert, but if you put in heat or energy or light, or if you put these under pressure, that can allow that double bond to break, and we're basically going to break that pi bond. We're going to pull apart those electrons, go into a high energy state, in their respective p orbitals around that carbon, and that at that moment when that is broken, then we can have the movement and the spinning of that double bond to form that new bond. So these can interconvert and we can create these cis to trans isomerism. And this is kind of I know here we have a halogen, but this is the idea that we're talking about when we look at processing some foods that have fat chains in them. Fats are long carbon tails, and you've probably heard of saturated fats versus non-saturated fats. The same concepts, the same terminology that we're using here. The difference, obviously, we're usually not using halogenated fats, but you can get a cis to trans isomerism. And that's where the trans fats, the concern with trans fats are. We'll talk about these later, but this is a way that we can generate them through heat and pressure, for example, and things that we generally want to keep out of our diets for reasons I'll chat with you about later in the semester. In addition to those high energy conditions with heat or light or high pressure, we can also have chemical reactivity with these double bonds in a form we call addition reactions. Now the p orbital, those pi bond electrons are more accessible and available, and they're also weaker than the sigma bonds. So those are the bonds that are going to react first. And you can see here with the addition reaction, essentially what we're doing is we're taking two things and we're adding them together. So the bonds of the double bond here are going to break, and the electrons in here are going to be creating new bonds between these A and B compounds that are then, those electrons are going to break apart these elements, and we're going to form with those new bonds. And we'll walk through kind of that process here in just a moment. You won't need to worry too much about this mechanism, but I do want to kind of show you how this works and what kind of things that are involved in determining what is going to happen with this type of reaction. First of all, I'm going to kind of draw out the carbons that are just kind of assumed to be here on the ends and the hydrogens associated with those carbons. And this double bond is actually going to be defined as a nucleophile. So when we have a different type of compound, we are looking for electrons are going to actually act in a way that they're going to look for a nucleus or positive charge. So these are, of course, p orbitals. These are electrons. They're going to be looking for something to interact with. When we have a situation where we have something that is going to be a electrophile, we're saying that it wants electrons. So electrophilic means electron loving. So this is going to be attractive. So anything, if we're looking at something that has a polar bond, so we have one component that's partially negative, one component that's partially positive, these electrons are going to be attracted to this positive bond. And that's why that arrow is drawn pointing at the electrophile. And the arrow of these electrons are going to be pointing towards the nucleophile. So this first step of the reaction is that we're forming a new bond between this carbon and that electrophile. So that's why it's labeled as an E. And then we have our nucleophile, which grabbed the electrons from this bond and formed over here. So you'll notice this arrow formalism. This is what we do in order to describe where the electrons are moving and how they flow. This doesn't talk about where protons are going or how that works. So it's a little counterintuitive for some people starting to look at these kind of mechanisms, but I just wanted to show you that this then forms this carbocation. So it's a positively charged carbon because this electron here lost the electrons in that bond to the electrophile. So now we have a positively charged carbon, which is called a carbocation, plus our negatively charged nucleophile. And the next step would then be for us to then have this nucleophile. We are going to have a positive charge here. So this has extra electrons, and I'll actually draw those out right here. And these electrons, or on top here, those are what are going to be attracted to that positive charge. And the next step would then have that interaction create that now bonded element. So we have two steps of this that are bonding. So this is kind of a generic example. And now I have a specific example here where we have hydrogen bromide, HBr, and we know that bromine is going to be more electronegative, hydrogen is going to be more positive, and what's going to happen here is the double bonds are going to be attracted to that positive charge on in that polar group, and the bromine is going to attack those or pull those electrons with it. And then we're going to, then after that step, the second step is going to be that bromine is going to attach to the other side. We can have two different possibilities depending on which way that, or which carbon that bromine attaches to. If we have it on the right side of the double bond or the left side of the double bond. We're not going to get into the details of this. Right now we're in this class. We're just going to say that, you know, it's an addition reaction. It's going to go one way or the other. The good thing about biochemistry when we get there is that this doesn't really matter, the major or minor product, because enzymes are going to help to decide which product is made. Enzymes are going to force the directionality of these types of chemical reactions. And that's kind of why we're not going to focus on it too much in this class. It's something that we focus on if you're going to do organic chemistry synthesis reactions. You want to be able to know what your product is going to be. We're not going to do that here. A little bit more terminology I want to discuss with you because it's going to relate later on when we talk about aromatic compounds is this idea where we would have cumulated double bonds, or we have double bonds essentially back to back to back, versus conjugated, where we have double bonds and then a single bond spacer between and then another double bond, or isolated. Now the reasoning for this is, or these different terms, is remember we were talking about these things requiring being unhybridized. So we pull out those p orbitals, and I'm going to just draw these above and below this cumulated example here. Essentially, these p orbitals are all going to be interacting with each other. Now, there's one set of p orbitals on that carbon that are shown, but if I want to interact with that middle carbon with the carbon on the right, I'm going to kind of draw this as a dotted line over here, this p orbital, and then this is coming out. You can kind of see that. And I'm trying to draw it in a way that kind of demonstrates its location, right? It's kind of pointing out at the screen, and then this dotted one is going back into the screen a little bit. And I'm going to do the same with this carbon on the right side, and then draw kind of shaded region just to kind of demonstrate that it's kind of going back into the screen. Now the blue set of p orbitals, that's our second set. So we have one p orbital here, and we have a p orbital on the other side that is going to be conjugated here and here. And so those are in two different planes. And that matters because electrons are they're kind of trapped in this area, or they're trapped in that other blue area, but they can't jump between the red and the blue area. But if we're looking at conjugated systems, I'm going to show you here, I can be conjugated, and these carbons can interact, and I can have another set next to it interacting in that same plane. And what actually this allows the electrons to do is actually allows them to flow through this whole area rather than just in one set or the other. So conjugated systems are really interesting and unique in organic chemistry because it allows for more room for those electrons to move around in. And whenever electrons have more space to move, then they're actually in a lower energy state. So conjugated systems, if we can create conjugated systems that provide some stability for the molecule. And here you can see isolated systems. I'll draw these two out in the same plane on the top. And we can move between these two systems here and here, but we have no pi orbitals or electrons or p orbitals here available. So these are not able to kind of flow through that middle because there's no electron orbital for it to flow through in that carbon. So those electrons again become isolated. So the system isn't any more stable than the cumulated system, for example. So there's extra stability in this center example. And we'll see this again when we talk about aromatic compounds. So how do we know if something's conjugated? There's going to be 3 unhybridized p orbitals in a row. And anytime we have a double bond, we're going to have an unhybridized p orbital. So I'll just kind of draw these out where we have double bonds on both sides. I'm going to draw these p orbitals out. And it looks like we have 1, 2, 3, 4 in a row. So that works. And then we also have an isolated system over here on the right side. So this would be conjugated over here. And just because we have more than 2, we have 3 unhybridized p orbitals. So we're not going to mess around with that too much, but I did want to introduce that concept to you as we move into the next section when we get into the aromatic compounds. So I showed you an addition reaction that included something that had polar bonds in it, like HBr. And we can also do this with hydrogen. So we can hydrogenate carbons, and usually we use some type of metal catalyst to do this. And that essentially turns this unsaturated carbon group into a saturated group. And the mechanism for this is essentially we can attach the hydrogens onto our metal. Their atomic radius is in such a way that when those are attached, they're going to be a similar distance apart as our carbon-carbon double bond. And they kind of organize and orient these 2 hydrogen groups in a way that allows for an easy bonding between the electrons in the double bond and that hydrogen on the metal. And then you can see it essentially pulls that off, and then we have a bond that is now saturated with hydrogen. So this is a mechanism for hydrogenation. We can do this with hydrogen. We can do this with halogenation as well. And a lot of times, bromine is actually a common chemical used to test for the presence of double bonds. If you have the red solution is the bromine solution. And if you put your perhaps unknown compound, if you don't know if it has double bonds or not, it will actually brominate this carbon compound. You can see that the bromine added to both sides of that double bond. And then that brominated compound will actually turn clear. So that allows us to understand that when it turns colorless, that it reacted, the bromine is no longer in solution, and it reacted with our compound that has double bonds in it. So this, again, relies on the polarizability of the halogen bonds, and this can then tell us about the product that we form. The next part of this I wanted to talk to you about is the formation of polymers. One of the most useful reactions of these small alkenes is a free radical polymerization that involves three different steps. Polyethylene, polypropylene, and polybutylene are all really common plastics used throughout society. So as we look at this reaction, we can, there are different uses for these in the food industry or in the science lab or even everyday uses for all sorts of materials. This is the initial radical addition reaction. So we have the initiation step happens first, and we typically have some type of organic peroxide. So a carbon group on the left, an oxygen singly bonded to another oxygen, and another carbon group. And so we can heat those up, and we are able to form a free radicals. And that is essentially where the oxygens each share that bond is going to pull an electron over, and we're going to form 2 of these new radical groups. This radical acts as a catalyst because it is not really happy in this form, having just 1 electron in that orbital and having an open one. So what we can do is these double bonds, these electrons will act as a way in order for which that oxygen can then create a new bond. So we then make this bond here between the oxygen and this carbon, and you can see that oxygen and carbon here have a new bond, and that free radical, that electron, now bumps onto the carbon. So the carbon now has a free radical, and then that is going to perpetuate additional steps. So this is the initiation step. So we initiate that free radical formation with a peroxide, which is generally a little less stable than most compounds, and we can heat it up to form that free radical to start the chemical reaction. Now we have the growth phase, and we've formed this free radical on carbon, and we have all these alkenes in solution, and this will just keep grabbing on, and that free radical is going to attach to this carbon with this pi bond electrons, and then we're going to form a new free radical that's shown here, and we're going to keep doing that over and over and over. And usually we're going to talk about the chain growth happens, and eventually we'll have termination as well when two of these free radicals come together. During the chain growth, branch points can be introduced if the chain wraps back around itself and grabs the hydrogen atom from the middle of the chain. These different chains and the different plastics are controlled by what peroxide initiator we use, different types of catalysts within that chemical reaction. We can different monomer types, so different starting materials, and then the different reaction conditions if we have it under pressure, under different temperatures. Those can all change different types of plastics that we're able to create. We're going to move on to alkynes, and they're very similar to alkenes, except for we have to unhybridize one more p orbital in order to generate another bond. So here we have the 180-degree bond angles, so they're linear. We have a single sigma bond and two pi bonds, and those two pi bonds are from two sets of unhybridized p orbitals. The bond length is a little shorter than double bonds, so we're at like 1.3 with alkenes, and we're at 1.2 with alkynes. So we compress these elements together a little more when we go to a triple bond. This picture on top kind of shows you a heat map, and that red tells us there's a lot of electron density in the middle here. So this is where we are going to be donating electrons to other things with our triple bonds. And we're going to see a lot of the chemical reactions are similar for alkenes. They'll also apply for alkynes as well. So we can use these in the same types of chemical reactions. Here's an example of halogen, bromine, and we have those attached to each other. We can essentially brominate our alkyne to make an alkene. And if we have extra bromine in solution, if we have two units of this in our solution, or twice the amount as our ethylene, then we can brominate it to completion, right? We'll break that double bond and create a single bond, and then the bromination here. So these can be stopped depending on the amount that we add, or we can create this whole process and break all of the second and triple bonds. We can also do hydrogenation the same way we did with double bonds. With hydrogen and platinum or nickel as the catalyst, we can resolve that triple bond back to a single bond. There's also different types of catalysts that kind of are called poisoned catalysts, and they can kind of only make that partially go back to a single bond. So there are ways that chemists can synthesize these different compounds. You have to memorize that, but just know that there are different ways to create these different molecules from the alkynes as well. One kind of interesting thing that we'll talk about when we get into different types of acids and bases, when we have carbons that are single bonded or double bonded or triple bonded, remember these are sp3 if we only have single bonds involved and it's attached to four things. It's sp2 if we have to unhybridize one of those p orbitals. So remember the numbers here that are related, we have one s orbital and three p orbitals that create four new types of orbitals that are bonding to our hydrogens here, or our organic compound on the left here. sp2, we have one s and two p's, and sp we have one s and one p. And that ratio is going to tell us how much s-like our orbitals are. And that matters because the more s-like it is, the more tightly carbon will hold on to its electrons. So it's kind of more of a spherical shape. Those electrons are held on tighter. So in sp orbital, the electrons on carbon are held closer to its nucleus. And that means it's pulling these electrons away from the hydrogen, and this hydrogen is easier to leave. So most of the time we don't consider carbon as an acidic compound with hydrogen, but when we get into this sp hybridization, this hydrogen can leave a lot more easily than a normal alkane can. And we'll again talk about that when we get into some of the discussions on acidity and acids and bases. And that's really where I wanted to end today with the alkenes and alkynes. And next I will talk to you about aromatic compounds and what those are and where we find those in our environment.